Welcome to an introduction to the Discrete Fourier Transform. I'm super excited to do this video series. This is a really amazing algorithm, and in this first lecture we'll just overview what we're going to cover in the series, and we'll do some basic Python code to see why this algorithm is so useful. So if you ever open a JPEG file on your computer, or ever play an MP3 song, or ever use the voice recognition of Amazon Alexa, or some kind of a music app like Shazam that recognizes music, then you have used some variation of the Discrete Fourier Transform. In fact, its efficient implementation, the fast Fourier Transform, is considered to be one of the most important and useful algorithms in computer science. And so in the video series, we're going to talk about how all of these is possible through the DFT. So the goal of the series is to understand the math behind the algorithm. We will also be able to use Python to analyze and manipulate audio files using the DFT. For example, even after this lecture, we'll be able to analyze the frequency content of a note or a chord played on various instruments. And then we'll be able to also filter out noise from audio files. So it's really amazing that we can do this really easily with Python. And the minimum requirements are pretty basic. So the complex numbers, basic complex numbers, and basic trig. If you've seen what a sine or cosine function look like, then that's really all you need for trig. We're only going to use basic Python, so if you haven't programmed before or have very limited programming experience, Python is very easy to read, very expressive, and very easy to follow. So we can just learn Python as we go along. So a lot of effort was made to make this as widely accessible as possible. And so I'm hoping to also make this available in my Algebra 2 and Pre-Calculus classes. But currently this is used for my AP Computer Science classes. Okay, so given a signal y of t, this is a continuous function on some finite domain from 0 to L. So for example, for us this would be an audio file. And because the signal is continuous, computers cannot store all that information, so we're going to sample from this signal at some sampling rate of fs, and we're going to sample it to get n total samples. And so we put those samples into an array. Y0 is the first sample, Y1 is the second, all the way to y of n minus 1. So graphically this is a continuous function, and so we're going to sample by picking out these sample points, and these sample points are picked out at equal time interval apart, and to get our n samples. So the discrete Fourier transform would take those n samples and convert it into another n numbers, but this time these numbers are complex numbers. And the way it works is that for each of these numbers are called Fourier Coefficient. To get each of those coefficient, we have to do a summation, and we basically take each of our sample and multiply it by something called a complex exponential. Notice you have I, which is square root of -1, and then so this is an complex exponential. And so we have this term by term products, and we sum them together to get one Fourier coefficient, and we repeat that for each of these coefficients. And so why is this useful? Well, it turns out that these numbers, the complex numbers, if we take the k coefficient and take the magnitude of it, so it's just the square root of a squared plus b squared, the magnitude of the complex number, it measures the amount that a certain frequency, fk, how much of that frequency is present in the signal. And so these frequency turn out to be just integer multiple of something called the fundamental frequency. So the fundamental frequency is basically is 1 over L, which is just one cycle over the time period 0 to L, and this set of frequency is just integer multiple of that frequency. And so these are precisely the set of frequencies that the discrete Fourier transform is able to detect from our signal. And so that's how we can able to analyze the frequency content of the signal. So again, if this is complicated, we're going to spend the whole series talking about the math behind this, as well as some intuition and a very geometric way of see why this amazing thing works. Okay, so now we're going to do some simple applications with it using Python. So if you haven't installed Python, it's recommended that you install something called the anaconda distribution, which has a program called the Jupyter Notebook, and we use Jupyter Notebook throughout this series. Okay, so here's the Jupyter Notebook. It actually runs on the browser, so this is the Chrome browser I'm using, and so we're going to be able to write code on this notebook. Okay, so this first line is optional, but allow all my graphs that I put to be inside the browser without opening up a new window. Okay, so I have a text file called the piano.txt. Contains sample values from recording of a piano sample at this 44,100 times a second. So in fact, I'll show you what the text file looks like. So it's just a list of numbers, just an array of numbers, and you can think of these numbers as the position of the speakers, and that means that the speaker has to basically vibrate or go to these position 44,100 times a second. So it has to vibrate that fast to be able to generate this sound of that piano. Okay, so we're going to load this data into an array and then play the audio. So we'll use the audio object, and then Numpy is a very powerful library for doing math, and so we're going to input Numpy as NP. Okay, so I'm going to now load the files np.loadText, and I'll give it the name piano.txt, and this will load the entire array into the variable ys. So for example, if I were to print out ys.size, it'll tell me that there's 100,000 of these numbers. And then I'm going to create an audio object using those numbers, so it's just an array of numbers, and I'm going to tell it how fast the sampling rate is, which is 44,100 times. And just like that, we have an audio object that literally make the speakers vibrate according to those numbers and generate this piano sound. So that's amazing how Python makes this very, very easy. Okay, we're going to graph this audio form. So we're going to have to learn how to use a library called Matplotlib. We'll input that as a PLT. Okay, to do this, I'm going to create n is the number of samples, so that's ys.size. Sampling rate is 44,100 times, so this is measured in hertz. And then the length of the audio clip is simply the number of sample divided by the sampling rate. So this is measured in seconds. So this is how long the audio clip is. So for example, if I were to print this out right now, I'll say that the audio clip is about 2.27 seconds. Okay, so to create a plot of this, I need the domain, which is the time sample, and then we already have the y sample from the file. So so I'm going to create a time sample. So this function called linspace from the Numpy library, and so because we have n samples, we also need n time inputs. So we're going to go from 0 to L. We're going to divide that interval into n points, all equally distance apart. So now we have the time and then the sample. So to plot it, I'm going to create something called a subplot. I'm going to call the subplot function from this library, and subplots will return two objects. The first object it will return is the figure that you can draw on. It also return an axis object that I can actually plot the points. So we're going to basically use the axis object to do all the plotting. So I can call x.plot, for example. I want to plot the input is ts, which is the time sample. The output is ys, which is the sample from the file. If I do that, I get the waveform of that sound. And so I can zoom in a little bit. So let's just try to do x dot. If I set the x limit, say I zoom in to say 0 to 0.1 second, so the first tenth of a second. Then so here's kind of a zoom in version. If I go further in, I say 0.5, then so this is the waveform. So for example, if I were to play the piano and record the pressure waves of that recording, then this would be the what the pressure wave looks like. Okay, so that's how we graph that. But notice that from this picture, it's hard to tell at least for me, it's impossible for me to know what this node is, because there's so much information and I can't see the content of this signal easily. And so the discrete Fourier transform take that signal, which is in the time domain interval, a time domain representation, convert it into a different representation, which is these coefficients, and these coefficients, as I mentioned earlier, right, measure how much content a certain frequency appear in the signal. And so let's actually create this frequency set that we talked about. So again, these are called the harmonics of the signal. And so the fundamental frequency we saw was 1 over L. In this case, let's actually do that. 1 divided by L. So this is the fundamental frequency. And so the discrete Fourier transform will be able to detect multiples of this frequency. So this is 0.44 Hertz. So I'm going to create, so first I'm going to create the K index. So K goes from 0 to n-1. So this is going to go from 0 to n-1. That's the index. So I'm going to say np.arange will return and put in n. So this will return an array of numbers from 0 to n-1. So in this case, 0 to 999,999 basically. Okay, so that's the index, and then so that's the K index. It's to get the frequencies. I take K and I divide it by L. Take the entire array of numbers, divide everything by L. So for example, if I were to print out the first few frequency, say the first 10 or something, from 0 to 10, then I notice I have the first frequency is 0 Hertz. The second is the fundamental frequency. This is the one we talked about earlier. And after that, notice these are all just integer multiple of the fundamental frequency. So this is 2 times the fundamental frequency. This is 3 times the fundamental frequencies, etc. And so this list of 100,000 frequencies are the frequencies that the discrete Fourier transform is able to detect from the signal. Okay, so we're gonna now do that conversion. We could use the Numpy's FFT module to convert those samples into the Fourier coefficients. So again, this is kind of high level. We're gonna be able to program the formula later, but right now I'm just gonna use it to do the computation. So we'll call these YK for the coefficient. So np.fft.fft, and I'll send over the sample. So given the sample, this is gonna convert it into an array of Fourier coefficient. So again, notice if I were to do dot size for this one, I see it's also 100,000 numbers. Okay, we're now going to graph the frequency domain representation of the signal, so we can see what kind of frequencies is present in the signal. Okay, so to do that, we're going to do the same thing as before, except that now our domain will be frequencies rather than time. Okay, so as before, we're going to just create the figure object and X object again. But this time, we're going to just plot the frequencies, right, that we saw we computed earlier, and then we're going to plot it against the absolute value. NP has an absolute value function of the Fourier coefficient. So now the domain is frequency, and the range is the absolute value of each of those coefficients. So if I were to do that, I get this. So this is kind of so notice that it turns out that we can detect frequency up to actually we sample at 44,100 Hertz, so we can detect frequencies up to that frequency. More on that later. It turns out that that's actually not true, but notice this signal is actually symmetric, so that there's content on the left and on the right. So again, we're going to talk more about this in later lectures, but right now I want to zoom into this so that we can see a better picture of, so set X limit. So I want to zoom into from 0 to say 5,000 Hertz. So again, the domain here is frequency, so I'm going to zoom into the first 5,000 Hertz. So now here it is. So this is a bit better picture. So now we see that there's some frequencies, there's some content at certain frequencies, and this is called the fundamental frequency of note, right? This is a little bit different than the fundamental frequency of the transform. Okay, so I'm going to zoom in actually a little bit further to kind of see what these numbers are. So I should do. Okay, so notice this says that in the homework for this lecture you can figure out exactly what these are, but right now from just looking at this, it's about a little bit over 500. So it's about 520 turns out, and 520 is actually the note for C5, which is an octave above middle C. And so notice that from this representation we can actually see what note it is, unlike the time domain representation that I showed earlier. And also this frequency up here is actually a multiple of that. And so and then this is 2 times the fundamental frequency, this is 3 times. And so really in fact these are called harmonics. When you play a piano, it doesn't have just one frequency. You know, the richness of the piano is because it has harmonics or overtones. And so this transform allows us to detect all of those frequencies that's present in the signal. And again, this is really amazing that only just a few lines of code we can mathematically extract the content of a signal. Okay, so just another illustration. So earlier we read in a text file. We can also read in a wave file. So this wave file is an A4. This is concert A, play on a violin. So let's so there's a wave file module from the SciPy library that we can use. So we're gonna say this can read in. So the file is A4 violin. So this will return 2 things. It will actually return the rate and also the sample. Okay, so again, I can create an audio object for this. The sample and the rate is given by FS. So it's also 44,100. So let's play that. There it is. There's the wave file. Okay, so earlier we plot a graph. So I just combine all the code from that into a function. So plot the signal as a function of time. And so the input here is the sample values, and I have here a couple of inputs, T1, T2. This is the time interval. So if I want to zoom into something, right, I can set my my 2 time beginning and ending time, and then FS. This is a keyword argument. It has a default value. In case if you don't send any value over to FS, then it'll give you, if you use this default value, but you can change it if you have a different sampling rate. So again, this code is exactly what we had earlier. I just put it here into a function so we don't have to keep copying it over and over again. So I also just set the label so that this is the time in seconds. Okay, so I'm going to run that. So now I can call the function. And we're going to be able to send over the YS that we got earlier from the violin. And then let's just say I'm going to go from 0 to 0.01 as a 0.5 or something. So this is the first half a second of the signal. So this is again is the violin. I can zoom in a little bit further. So if I keep zooming in, notice so here it is. But the idea here is that again this representation, the time domain, it's hard to see what it is. So we're gonna create another function, the plot signal sequence. So this is you plot in the signal, but as a function of the frequency. So this is actually very similar to the other one, and so but this gives you a chance to kind of see that code again. But so again, I need the size of it. I also need we have the sample rate already. I also need the time, which is the size divided by sampling rate. Then we're going to convert use FFT to convert our sample to the Fourier coefficient. Then we create our array of indices. So np.arange. This will go from again 0 to n-1, and then from that we can create our frequencies. So take k divided by L. So we saw this earlier. So now we can plot it. So we create again figure and axis object. So this is just a review of what we just did. So again, so this video we're going to learn Python as we go, and we're going to learn how to do these things by example. So so in the homework you get to kind of redo some of this and learn how to do this and be able to work on some problems. Okay, so we create those two objects, and now we can plot it. So ax.plot. So now again we're plotting. The domain now is frequency. So here's the frequencies, and absolute value of the coefficient is the range values. And then I want to just again we want to zoom in. So this frequency allow it to zoom in into a smaller frequency. So again, set x limit to f1 to f2, and then if I want I can also do some labeling. So set x label, for example, and I'll call this label be the frequency, right, measure in hertz. I'll set the y label as the absolute value of the Fourier coefficient. So I think that should work. So this function can now help us plot the frequency domain. So let's do that. I'm going to call the function, and I'll send over exactly the sample value from the violin signal, and let's look from 0 Hertz up to 5,000 Hertz, say. So there it is. So this is a little bit more complicated. It has a lot more frequency content. So okay, let's actually zoom in a little bit more and just say maybe like 3,000 or something. Okay, so notice here, again, as part of the homework, you're gonna figure out exactly what these notes are. But this is about 440. In fact, this is exactly 440, and 440 is, as you know, A4. And so this frequency here is A80, which is 2 times that. So that's an octave above A4. So that's A5. This one right here is about 1320, and 1320 is actually E6. So the note E6, and this right here is I guess twice A80. So this is an octave above A80, which means that this is I guess A4, so A6. So this is A6, and then this one right here is actually about 2200, and 2200 is a C7, a C sharp 7. So we have an A, an E, and a C sharp. So that this is actually is a violin playing an A major chord. So this is, I think this is so amazing that we can just like within a few lines of code mathematically extract that the violin is playing a certain chord, right? I think that's really awesome. And okay, yeah, so that's basically so in the, well, actually here's another example I have here. I actually created so I have a trumpet note that I added to that trumpet note some noise. So I added something called a linear trip, which basically is just a bunch of a sinusoid that goes through a whole range of high frequencies. And so by adding this in, I just have a trumpet that has some noise in it. So let's just actually play this. So you hear the trumpet and you hear some kind of annoying high frequency noise. So as part of the homework for this assignment, this first lecture, you get to filter out that high frequency noise and create a new wave file that has only the trumpet. And then your other problems for this lecture is to analyze notes and chords from different instruments. And so there it is, first video, but we get to do a lot of really, I think, cool things. And as you can see, you can really be able to duplicate all this. And so if you go to my website, I have all these data files, this notebook, all the sample code, and then as well as all the problem sets. And so I just want to end with all the references. So these are great books that I've used to kind of learn about these things. But I do want to point out, I want to thank Ryan Soklaski from MIT Lincoln Lab. I was his assistant instructor for a program called Beaverworks Summer Institute last summer, and he's the one that showed me all this stuff, which is kind of, so I appreciate him. Yeah, so please come back. The next few videos we'll talk more about some more applications and some math behind why this algorithm works. Thanks for watching.